Hi, my name is Tiffany Laij, and this is Physics 2211, lab number 3, black holes. The purpose of the first part of this lab is to calculate the mass of a black hole that's customized by an email seed by analyzing the orbit of a star. In part 2, we will use this calculated mass to find the initial velocity of a ship so we can fly from the planet around the black hole without crashing. We will go over physics concepts, the computational setups for both of these, and the analysis. So the physics concepts and principles for both of the parts of these labs rely on two things. Newton's law of gravitation, which basically says that the force of gravity is equal to g times the two masses for objects over r squared, which is applicable to both part 1 and part 2 of this lab. Next is Newton's second law of motion, which is basically to calculate the change in momentum over time, or the velocity, which is dp over dt is equal to f of net. We can use this to find the mass of the black hole, and also in order to find the initial velocity in the second part of the lab. We will also be using centripetal force, which is mv squared over r, in order to figure out the circular orbit of both the planet and the spaceship over time. We will be also using the velocity and position update formula in order to do this. So to determine the mass, we will basically do dp over dt, which is the rate of change in momentum, and we will get this by doing our force of gravity, which is g times the mass of our star times the mass of our black hole over r squared. These are both f net, so we can equal them to each other and rearrange that in order to substitute into our mass of a black hole as we substitute from the force of gravity. To determine the velocity of our spaceship is basically we're going to calculate the net forces on the planet and the ship since they are both moving. This is through the superposition. And then we will get our centripetal acceleration that it's going to be able to keep our ship in orbit and not just go hang wire. And then since gravitational force is what causes the centripetal acceleration, we equal them together and then substitute to find our velocity. There's going to be a lot of different options for this, and we're going to find this through trial and error. So for the first part of this lab, the main results of our lab and our findings is that the mass of our black hole is 1.5928 times 10 to the 31st. We can show that our f of net and our parallel and perpendicular components are here. Our computational model. So our initial conditions and constants of it is that the star is our system and surrounding is everything else, which is basically just the black hole. And so we are given our mass of our star and our gravitational constant, and we're also given delta t, which is basically 1 day between each point, and our first observation is t equals 0. We find our black hole basically from our seed in our email. In order to find the mass of the black hole, we basically use a lot of formulas. As you can see here, P equals mass times velocity is used to find the momentum. In line 169 and 170, we find the change in the velocity and momentum in order to calculate dp over dt, which is basically our f of net. And over here, we calculate our dp over dt parallel by multiplying this by p hat, and we calculate the perpendicular vector by subtracting the parallel vector from the total net force. And all of this can help contribute to the f of net, which is basically giving us the mass of our black hole by rearranging the f of g equation in order to get line 194. In order to find our actual average of our mass of our black hole, we basically sum up all these points and then divide it by the total number of points that are calculated. For part 2 of this lab, the main results from our finding is that the initial velocity of our ship is equal to negative 1.3 e to the 7th, 9.325 e to the 6th. In our computational model, in order to find this, is our initial conditions and constants is our spaceship, our surroundings is our black hole and our planet that are putting force on it, and then over here we've shown that our other constants that are shown. In order to calculate the initial velocity, we need to find the net force on both the planet and the ship. So these are basically the same thing, which is f of net is equal to the force of the black hole on the planet plus the ship on the planet. As you can see here, and it's used from the gravitational equation. This is the same thing for the ship, where we find f of net on the ship is equal to the force of the black hole on the ship plus the force of the planet on the ship. To find the velocity, we basically use 109 and 110 to update the velocity and the position of both the planet and the ship. And then we find this through trial and error, and as you can see, this is what I got. So possible discrepancies and errors in the analysis of both of these labs is that it's not used as relativistic momentum, which is probably a better way in calculating both the mass of the black hole and the velocity of the spaceships, since all of this is occurring at very high speeds. We also use assumptions that we calculate that the ship and the planet and the ship was moving around, but the black hole could also be moving around, so we would have to calculate that as well, since they're all moving at that point, and there could be other external forces. So what does it mean? What's the difference between net force and the rate of change of momentum? So these basically go hand in hand and are basically the same number, but they refer to different points. So net force and its components are the cause of the change of momentum, whether it's force of gravity or the force of spring. The change in momentum dp over dt is actually the effect of the force, which is basically when the force is put on, and it's measured in kg over ms or mv. What if? What initial velocity would your spaceship need in order to orbit the black hole without crashing? So basically, I did a lot of trial and error, and it initially travels outward of the planet to avoid a crash. Thank you.